Okay, welcome back, everyone, to the Innovation Hub, where we have arrived at our final presentation for today, and it's going to be by Maurits Korthals Altes on behalf of Avalor AI. He's going to introduce you to AI for military robotics, and he has assured me that this drone will stay stationary, so no need to worry there. Maurits, the floor is yours.
Good afternoon, everybody. I'm Maurits Korthals Altes, CEO of Avalor AI, and today I would like to start this talk with a story that was shared to me by my former commander when I worked at the army as a student employee. So, let's start. Imagine the following. It's September 2006, Uruzgan, Afghanistan. The Dutch peacekeeping mission is fully deployed. In a small village east of Deir Hawood, a convoy of 11 vehicles rumbles through the riverbed back to base. In the back seat of one of these vehicles, you doze away in the intense heat. Suddenly, you are ticking on the outside of the vehicle. A screen in front of you flicks on with a warning: enemy fire. Before you have time to react, drones take off from the roof of your vehicle, and you hear the loud noise of unmanned vehicles positioning themselves between you and the source of the enemy fire. Bang! With a loud noise, a rocket slams itself into the thick shield of one of the unmanned vehicles protecting you from harm. Close one. You take a deep breath, regain control of yourself, and start marking targets using the autonomous drone swarm overhead. Time seems to stand still, but within 15 minutes, your team has regained control of the situation. Thankfully, nobody was harmed. Now, of course, the story I just shared with you is a fictional story. The real story, as told by my commander, was in the same setting, the same ambush, but lacked the autonomous systems. Instead, they relied on chaotic radio chatter, printed maps, and exposing themselves outside of the vehicle to gain some visibility. Although their response was decisive, multiple rockets hit the convoy and one of the drivers lost its leg. Therefore, our goal at Avalor AI is to make this first fictional story a reality. So how do we achieve that? The first thing we should note is that compared to 2006 from the original story, unmanned systems are already playing a very important role in modern battlefields. This is exemplified, of course, by the proliferation of unmanned aerial vehicles in Ukraine. Now, in Ukraine, these drones are mainly used for intelligence, surveillance, target acquisition, and reconnaissance, called I-STAR missions in military abbreviation. Now, this means that they can be used to predict the courses of action of enemy movements, plan your own movements, maybe prepare even an ambush or call in air support or artillery strikes. Now, no one can deny the usefulness of these systems, but still we cannot make this story I shared with you a reality. And that is because we have five challenges still surrounding the deployment of unmanned systems. The first one is that there remains a risk of being located, because you have to operate the system, you emit an electromagnetic system, and so the enemy can locate you and target you. The second is that you have a low situational awareness. As you can see on the images, you see that the operator is really fixed to a screen and has no time to look at its surroundings. The third one is that you have limited scalability. Only one operator can control one system at a time. The reverse is also true. Because one system is controlled by one operator, that means that if you lose the operator, you lose the system. There's minimal redundancy. And the last one is that there is a risk of mistakes due to operator fatigue or exhaustion. Now, we believe at Avalor AI that AI is a method of solving these challenges, and therefore our mission is enhancing the tactical value of autonomous systems by increasing their autonomy with AI. Now, of course, we understand that deploying AI is surrounded by ethical, moral, and legislative issues. Therefore, today, in this talk, I would like to answer 3 questions from an engineering perspective. First, I want to talk about how do we as engineers define responsible AI. Second, what AI technologies are we using, how and why? And lastly, how do we approach the challenge of developing responsible AI? So first, the theoretical part. I will promise you it's a short part. We'll get to the practical stuff very soon. The definition of responsible AI. Now, I've split this in two parts, responsible and AI. First, responsible. As an engineer, there are two main metrics important for defining if something is responsible. The first is the quality or the performance of the method, and the second is explainability. Now, a way of explaining quality of a method can be visualized with precision and accuracy. Precision means how close the answers are of a given method, which you can see on the x-axis. You see to the right, the answers of a method are clustered close to each other. The accuracy is how right the answer is on average, which you can see on the y-axis. Now, a responsible method is the one in the upper right. It's almost always right, and the answers are very coherent, close to each other. An irresponsible method would be the one of the lower bottom. There you can see it's not accurate and not precise. You should not use it. Now, the second one is the metric of explainability. Of course, this is a metric we have seen and talked about a lot today, but I want to view it from two perspectives: the liability and the trustworthiness. Now, the liability, the accountability, is one that was also highlighted in the plenary session this morning. We know that we want to be able to point out to someone if something went wrong, who is to blame. But the second one, trustworthy, is a very important one too, which was shared by the general this morning. Now, this one came from our cooperation with the military. You have to visualize that if you want to employ a method in AI, a military operator needs to be able to trust it at any time in any given circumstance. And this makes sense, because also in the military itself, before you go into an operation, you have months and months and months of training with each other to be able to trust each other even in the most chaotic of the chaotic situations. Now, this same holds true for AI. It should be explainable not only for the accountability and the liability, but also for its trustworthiness. Now, the second definition, AI. Now, there are many ways to explain this, and for today we have tried to define three main concepts along an axis of explainability. This is by no means the only way you can classify different types of AI. It's also not exhaustive, nor technically completely correct, but it will serve for today to explain the concept of responsible AI. We start on an axis of explainability with the best explainability. This is rule-based. With a rule-based approach, you have a limited set of inputs and a limited set of outputs. I know exactly what can happen under any circumstance. Most people know this by, for instance, a decision tree, which is also a concept widely used outside of programming. The second one is the approach of optimization. Here you still have a limited set of calculations, but the outputs are continuous. So how do I visualize this? It means that I have some kind of knobs to turn from an algorithm so that I can tune how it works. And although I have some control over these calculations, I never know in each situation exactly what is going to happen. It's less explainable, but we can do more. The last one is the pattern recognition approach. This is often known as machine learning, deep learning, reinforcement learning, in general, black box models. Here we have a continuous set of inputs, the data, and a continuous set of outputs. We don't know much what is happening inside. It's the least explainable. Now let me explain these concepts from a military example. So today we want to view these methods in a target recognition example. The goal here is to identify if something is a military target or not. So how do we do this? For today, we assume that you can positively identify a military target if it has camouflage on it. As input data, we will use RGB images. This means an image with pixels, and each pixel has 3 values. Now we know RGB mostly from lower school, from the 3 colored circles. Each of these pixels has a value for red, green, and blue, and so we can mix up those colors. So the first method, rule-based. How would we do the target example with a rule-based approach? We are going to divide the image in sections of pixels and average the color. You can see that on the lower bottom. Then we simply say one rule. If the average green value is above the value, for instance, 150, then we label it as a target. So how would this work in practice? We can see the results. For instance, on the left, you can see an image where it has positively identified a military target in a sandy environment, but also a civilian. It didn't work. In the right image, you see that it has positively identified the target, but it also made false positives or fake targets of the bushes and the trees. So we can say that the quality of the method is low, but we know exactly why it has failed or why it has succeeded. It's just simply because of the rule of the green value. So let's try a different method, the optimization one. We take the same images, but we are going to make an algorithm that iterates over each of the pixels. Then we are going to find chunks of pixels with roughly the same color, like you can see in the images below. Then we say we add another computation where if there are sufficient patterns within each chunk, we can say it has some stripes or spots. It must be camouflage. And again, we want it to be green, unlike the tiger displayed here. So how does it perform? The quality has improved in the left image. You see you have a military target and the civilian is not identified anymore, possibly because it doesn't have a camouflage pattern. On the right, we see less false positives, less trees, less bushes. But we also see that the target is not identified anymore. And here you have the complexity of the optimization method, because which of the knobs are you going to turn to redetect the target in the right image, but prevent that you, for instance, will redetect the civilian in the left image? We can make some assumptions, we can turn the knobs, but we never know completely for sure. So that's the reason it's a bit less explainable than the first method. So we go to the third one, pattern recognition. In this case, we select a black box model which is suitable for this problem. In this case, supervised deep learning. This is displayed with the image below. We have a lot of data sets, and we can train this black box, this model, so that it will eventually deliver us one model we can use for new input images. Now we can make some influence, we can have some influence on the model we select, and maybe some overarching parameters, but the resulting thing that comes out of it, that makes the calculations, we cannot look inside it. We cannot explain it. So how would this work? Well, we see the quality is very high. In both images, it has successfully detected the target. So is this then the best method? Well, as I said, with pattern recognition, the explainability is the lowest. So why is this actually the explainability is the lowest here? Why doesn't it work for any situation? Well, to explain this, I want to show you an example, a very famous example, some of you might know it, about huskies and wolves. In this case, there were researchers that tried to develop a machine learning algorithm to detect huskies from wolves. Now, we see in the left images that most of the time it's correct. However, at some points it is not. And they tried to find out why is that the case. Well, they dug deeper and found out that instead of classifying the differences between huskies and wolves, the pattern recognized was if images were taken in snowy or non-snowy conditions. So actually, they made a black box model that detected snow instead of huskies. So that's the point. You never know for sure how it's functioning, although the quality might be good. So given that we have seen these different levels of explainability and quality that both contribute to the responsibility of the method, what method should we choose? Well, we can first conclude that the explainability is tied to the method itself, but the quality differs per use case. In this example, we can see that the quality was highest with pattern recognition. Now we know for a fact from military requirements, and we've heard it all day long, that especially with target recognition, there's always a human in the loop. So we have a mitigating measure here. We can select the pattern recognition method, and although it's not explainable, we can still use it for high effectiveness. But how does this generalize in other projects if you are going to develop other AIs? Can you make the same assumptions? Well, I want to explain these assumptions and how we use them in a practical application through one of the projects we do for the Dutch military. Now, I will explain this first and then dive deeper into the AI methods we have used there. So Project Spear is that of making a drone swarm in a consortium with TNO, Delft Dynamics, Tactive Robotics, and Avalor AI. where we deploy a fully automated drone swarm that can do the battery swapping itself autonomously, the airspace management surrounding it, target recognition, searching, swarming, cooperation, and everything you want to make an autonomous mission with drones. Then it will simply give you the results back in a battlefield management interface. The interaction is minimal. So for the specific features we have developed here, you can split them along 3 main concepts, along the military requirements that are used for these different concepts. Now the first one is that the specific system, the drone swarm, needs to behave, do certain drills, behaviors, and procedures. Now this is, for instance, airspace management. It's very simple to, very similar to an air traffic controller in an airport. You need to be able to control the aircraft where they go. You don't want them to collide, so that's a reason to have some specific procedures. For these, you want them to be absolutely trustworthy and clear, and there are no unforeseen circumstances. For the second, for planning and scheduling, you can think of the searching with a swarm. In this case, it's a very dynamic environment, and there are many unknowns. Furthermore, you want a hands-off experience. The operator needs minimal intervention. The last one is sensing and perception. For instance, the target acquisition. In this case, it should perform very well, but we know that the human in the loop is almost present. So let me give you an example of our selection of different AI methods. The first one, airspace management. Here we know that multiple drones might want to, at the same time, change their battery. So how do we fix it? Well, in this case, we have chosen the rule-based method of a behavior tree, a general concept which you can lay out different options and arrange them all in a specific order so you know exactly what is going to happen. At any time, an operator can see in which state a specific system is. So it's rule-based, it gives you insights, and it performs very well in specific scenarios. Another method we wanted to use for another feature is the cooperative path planning. In this case, you have a large area of different sizes, different terrains, with which you need to cover with your drones this area. Although you do not only have to search, you also have the scheduling in between. For instance, if a battery runs low, you might have to return. But if you are following a target, what do? Does one of the systems stop with searching, and does it take over the target? How do you solve that? For this case, we have chosen an optimization method. In this case, the operator does not need complete visualization of the decision process, only to see the results. So the last one we have already touched, of course, is the classification and tracking. In this case, we know a human is always in loop, and the method should minimize the amount of false positives. So in this case, we can safely choose the pattern recognition approach. Now, having seen this, can we say something, conclude something about what type of AI we should use? Our conclusion is that there is no such thing as responsible AI, only responsible use of AI. And this is the case because we see that responsibility can be defined along its axis of quality and explainability. And although explainability is tied to the method itself, the quality is not. It's depending on the use case. Therefore, there's no golden bullet in AI methods. You should choose it based on the specific use case in cooperation with the military. Now, the main force behind this, driving this, are the military requirements. And therefore, my concluding remark is that at this summit, it's our responsibility to create a clear understanding of the military requirements so that this can lead to the next step in responsible use of AI. Thank you.
Thank you very much, Maurits. I think the first conclusion I draw from your talk is that we need to rename our conference slightly to REAIM, because there is no responsible AI, but only responsible use. But I'm sure the audience has more intelligent questions than that. So if there are any questions, please raise your hand and I will come to you with the microphone.
It was a clear talk then.
Hi, Maurits. For the last AI, you said you used a hidden model. I think it's a neural network used. But for that, there's already algorithms that can determine which nodes your algorithm picked, of your AI picked for the decision of your image. So actually, that's quite explainable.
So
when you see a picture of a husky, it says, okay, I looked at the ears, I looked at the mouth, and then it can decide. You can see, okay, why did it pick a husky?
So yeah, the question about that there are actually methods, and I showed them actually in the presentation that you can explain some methods, especially the black box ones also. It's true, but that's more from a perspective of liability, but explainability is also tied to the trustworthiness, and maybe you are able to devise something that can, in a later stage, exactly say, okay, these pixels for this reason have made the decision to select this as a target, but that's not insightful for an operator in a military operation. I mean, you have a lot of noise around you, the bombs are falling, you have to make a decision, and then it gives you the generated result. So it's not explainable at all at that moment, in contrast to rule-based methods.
Other questions? If not, thank you very much, Maurits. Fascinating talk, and I think a good call to action on all of us at the end there. So let's use tomorrow to further dive into the I think complicated questions surrounding use of AI in the military domain. This was our last talk in the Innovation Hub for today. So thanks to all of you for being here. I hope to see you again tomorrow. Enjoy the rest of the conference and have a good evening. Thank you.